Thanks for the invitation to talk. So like Paolo said, our goal, at least my goal for the next two talks at least, but maybe all the rest of our talks too, is to we want to produce minimal models of foliations on threefolds. Foliations on threefolds. So I think at least for my next two talks, I'm going to try and explain the proof of the following theorem. I guess I should mention that these, basically everything I'm going to be talking about is contained in these three papers up here on the archive. So the theorem I want to prove for you guys is basically the existence of co-rank1 foliations on threefolds. So let's let X be a projective threefold, and F is a co-rank 1 foliation or co-dimension 1 foliation, I guess, depending on your preference, with simple singularities. Then there exists an MMP for F. So just to recall what that means, because I guess Paolo explained what that means for us, is there exists a birational contraction x to x prime. So phi is a birational contraction, and actually it can be factored as a sequence of precise surgery operations. And I guess it only contracts curves tangent to the foliation, so it modifies the foliation leafwise, such that one of the following happens. So either we have a minimal model, so kf prime is nef, and f prime is just the strict transform of f, or we're in the Mori fiber space situation. So there exists a morphism called little f from x down to z, such that minus kf is f ample, and the fibers of f are tangent to f. So somehow our foliation contains lots of fauna varieties in its leaves. In particular, there's some algebraicity to the leaves of the foliation. So I guess I want to make a quick remark. Is that actually that we can actually prove a much more general statement, so we can prove this for FDLT pairs, whatever that means. I'll probably try and talk about what an FDLT pair is in the next lecture, but right now we won't focus on those, but there is a more general statement. So today, today, I want to talk about the cone theorem. So I guess Paolo mentioned what the classical statement of the cone theorem is. So I want to explain the following theorem, so cone and contraction theorem. And so somehow this is the theorem which sort of guides our surgery process that we do in the minimal model program. So let X be a projective threefold again, and let F delta be a log canonical pair. And I'll define what this is in a bit. Then we can write the Kleiman-Mori cone, any bar x, as a sum of two parts. So we can write it as the part where kf plus delta is positive, and then we can write it as a sum of a lot of extremal rays spanned by classes of curves Ci. And so what we have is we have Ci is a rational curve tangent to f. And even better, we have the following inequality. The negative kf plus delta out of the Ci is of bounded negativity. Moreover, if f delta is a canonical pair, again, I'll define what that is in a bit, then there exists a contraction morphism. Associated to our extremal array. For all I. Okay, so somehow this is the first ingredient we need to produce minimal models. Okay, so I guess the first thing I want to talk about in the proof of this statement is I want to do a recollection on singularities of foliations. And this is sort of a mix. This also includes some facts about, the classical theory of singularities in the minimal model program. So recall that a foliation, at least for me, is defined by a coherent subsheaf of the tangent sheaf. And we can define the canonical class of the foliation is just the determinant of TF dual. Now, if you're given a birational morphism, or actually maybe what I want to talk about here, maybe I want to say this. I want to make a quick aside, a quick definition. So let D inside X be a divisor. We say D is F invariant, provided, well, we have natural inclusions, TF restricted to D, mapping into TX restricted to D, so that's just the natural inclusion. And we also have, the natural inclusion this way. So we say it's F invariant provided there exists a factorization like this. Okay. So now, given a birational morphism, let's say X tilde to X, so birational morphism, weird. Okay, yeah, so let's say, so there exists a birational morphism, and we get a transformed foliation on X tilde. So we can let F tilde just be the strict transform of F. Now, what we know is we can write KF tilde as equal to pi star of KF plus some sum AI EI, where EI are the pi exceptional divisors. Now we say that F has canonical singularities provided AI is bigger than 0 for all I and pi, so all birational morphisms and exceptional divisors of these birational morphisms. And we say that F has log canonical singularities. Provided that AI is bigger than, so 0 if EI is invariant, and bigger than -1 if EI is not invariant. So in particular, if we have a foliation such that all the exceptional divisors are invariant, the notions of log canonical and canonical agree. There's one final class of singularities I want to talk about, and those are simple singularities. Because somehow a careful analysis of these plays an important role in our proof. So let F be a, so I guess I should say the above definition doesn't care about the rank of the foliation or the dimension of X or anything like that. That's just a totally general way of classifying singularities. Simple singularities are particular to co-rank1. So let F be a co-rank 1 foliation on a germ of Cn. And we say F has simple singularities provided that formally about 0, F is generated by a 1 form of the following form. So somehow it's just defined by some canonical local forms for the foliation. So either what we have is it's defined by one form of the form lambda dxi over xi, such that, and we have a resonance condition, ni lambda I is equal to 0, if and only if, so I guess, and the ni's are all non-negative integers, if and only if ni is equal to 0 for all I, or where it's of the following form, so I guess I'm going to say I is equal to 1 to s, and I is equal to 1 to k of pi dxi for xi plus psi x1 p1 xk pk, and let's see, I is equal to 2 to s of lambda I dxi over xi. And again, we have the same resonance condition on the lambda I such that ni lambda I is equal to 0 if ni is in if and only if ni is equal to 0 for all I. So one remark I want to make, or actually maybe two remarks, is that the only formal invariant divisors for the foliation are exactly these coordinate hyperplanes. So so this guy is the only invariant formal hypersurface. So remember, this is just a formal. This is just formal locally. And the warning, and the thing we're going to see, this is going to cause us problems later, is that not all of these hypersurfaces you can't necessarily choose a convergent set of coordinates for all these hypersurfaces. So not all the xi are convergent, or at least not necessarily. So some of them might only exist formally locally. So we won't have to worry about that so much today, but tomorrow, when we talk about existence of flips, this will be a serious thing to consider. Okay, so I think that's all I want to say about foliation singularities. So we have, these foliation singularities, this way of classifying foliation singularities, which come from the minimal model program. This notion of canonical and log canonical. And we also have this more classical notion of foliation singularities for co-rank1 foliations. I guess I should also remark is that in dimension less than 3, we can always resolve a foliation to one with simple singularities. And these are results of Seidenberg and Kano. But in higher dimensions, this is, at least to my knowledge, this is very much open. And this is part of the reason why everything we say is restricted to the dimension equal to 3 case. Okay, let's see here. So I next want to, Paolo talked about this theorem a bit, but this notion of bend and break, but I need it in a slightly different form than the way Paolo talked about it. So this version of bend and break that I'm going to write down for you guys is basically the form, a form of bend and break, I guess written down by Kiel, Mitsuki, and McKernan, and I guess also involves some work of Mioka. So what it says is the following. So let's let X be a projective variety. And I guess normal, but otherwise we don't care about the singularities at all. And let F be a foliation. We don't care about the rank or the singularities of the foliation either. So it's a very general statement. And let D1 through Dn, where n is equal to the dimension of X, be Neff Cartier divisor, or Neff Q Cartier divisors. I guess actually R Cartier is okay. Such that D1, so their product is 0, and the product of minus KF with D2 dotted Dn is positive. Then X is covered by rational curves. But it's a bit better. So cover rational curve sigma, such that, well, 1, negative kf dot with sigma is positive. So they're all kf negative rational curves. They're also, they're also all tangent. Tangent to F. And finally, we have that D1 dotted with sigma is equal to 0. So I don't want to prove that, but it's a very nice theorem, and it's somehow a very vast generalization of the theorem that Paolo explained to us in his talk. Okay, so we'll come back and use that later. The next thing I wanted to talk about for a bit is this idea of adjunction. And philosophically, I mean, what we want to do is so let D inside X be a divisor. And again, everything I'm going to say in this section is independent of dimension and rank of a foliation. But we'll only use it basically the co-rank1 case, but this is all just a very general set of general facts. So let be a divisor and F a foliation. So what we want to do is we want to compute KF plus epsilon D, D restricted to D in an intelligent fashion. So intelligent way, whatever that means. So let me define epsilon D. So epsilon D is just an indicator function for invariance. So epsilon D is 0 if D is invariant, and it's equal to 1 if D is not invariant. Okay, so somehow we have two different cases of adjunction, right? Corresponding to whether or not the divisor is invariant or not. So let's think about these two separate cases, and we'll try and see what we do. So let's first consider the case where D is invariant. Well, by definition, we get an induced foliation on D. So by definition, we have a morphism. TF restricted to D mapping into TD. And we can double dualize everything. So we get a map. And this still maps into T double dual, but because the tangent sheaf is always reflexive, this is just TD. And this corresponds to, I guess, a restricted foliation. It's an induced foliation. And induced foliation on D. We'll call it F D. So now here's a fact that one can check, is that KF restricted to D is going to be equal to K of FD plus delta D, where delta D is an effective divisor. So we don't actually get that KF restricts to KFD. There's a bit of there's a difference between the two, and that's given by this effective divisor. And I guess and observe that delta D is supported on I guess the singularities of F intersection with D, at least in the case where X is smooth. Okay. I want to make a quick remark about this, is that let's consider the special case where the dimension or the co-rank of F is equal to 1. In this case, K of FD, well, FD is just the trivial foliation with one leaf in this case, right? So K of FD is nothing other than K of D. And in fact, we can prove a slightly more precise statement. So let let S be, well, maybe I want to say, let SI be any collection of F invariant divisors. Possibly even formal. This isn't such a big deal. Well, we also have, the classical adjunction statement. We can write K of X plus D plus the sum of the SIs. Well, we can restrict this to D. And we'll write this as K of D plus theta of D. And what we know is that theta of D is effective. And this is just the classical adjunction formula. But the interesting fact is, so what we can observe, and this will be important later, is that delta D, so the foliated different, is always larger than the classical different when we do this computation. So this will be important later. Okay. Now let's consider the case where epsilon D is 1, so D is transverse to the foliation. So in this case, again, what we can write is, well, I should say, so in this case, we also get an induced foliation on D, given by restriction, given by restricting the one forms defining the foliation. So, and the foliation can be defined by a subsheaf of the cotangent sheaf of X. And what we can do is we can consider the map and we can look at the image. We'll call this psi maybe. And so the image of psi defines a foliation on D. And we'll call this foliation FD. So I guess observe that in the case where epsilon of D is equal to 0, so D is invariant, the induced foliation has the same rank as the ambient foliation. Whereas in the case where epsilon D is equal to 1, so D is transverse, the induced foliation has the same co-rank as the ambient foliation. And we have the following quality: Kf D plus D restricted to D is equal to K of FD plus delta D, where again, delta D is a canonically defined divisor. Defined divisor. And I guess a quick remark is that if the pair FD is log canonical, then FD delta D is log canonical. I guess also another just kind of silly version of this is that if the rank of F is equal to 1, and FD is log canonical, then what you can actually check is that Kf plus D restricted to D is actually linearly equivalent to 0. It always vanishes. And that's just because K of FD, in this case, is the foliation by points. Okay. So I think now we have all the basic sort of technical widgets we need to prove the cone theorem. And I'll try and give a quick sketch of that. So the idea is this. Well, here we have, let's just assume that delta is 0. So we have no boundary whatsoever. And we just have KF. Well, we have the positive part of the cone, which of course you don't know anything about. But then we have, this negative part of the cone. And what we want to do, I guess like Paolo drew for us, is we want to draw some supporting hyperplane, which meets some extremal ray R. And we'll call this HR. And we can write this as KF plus A, where A is ample. And our goal, show R is spanned by a rational curve. Okay, so we have a dichotomy. Either HR cubed is equal to 0. So HR is Neff. So, it's a Neff divisor. So either HR cubed is 0 or HR cubed is positive. So it's big or not big. Let's look at case 1 first. So in case 1, we want to apply bend and break. So what we want to do is we want to apply bend and break using, so let's say with DI is equal to HR for I guess, less than the numerical dimension of HR, and DI is equal to A, our ample divisor upstairs that I wrote up earlier, for I guess I between 3 and the numerical dimension of R. So you can check, it's not hard to check the hypotheses of bend and break are satisfied in this case, and this produces rational curves sigma such that sigma dotted with HR is equal to 0. But this implies exactly that the class of sigma is inside our extremal ray R, which is what we need. And it's not hard to check that these, I guess by construction, these sigma are tangent to the foliation in the rational, and it's not hard to check that they have bounded negativity. In case 2, we want to proceed by induction on dimension. So observe that we can write HR, because it's big, we can write it as a sum of an ample divisor plus an effective divisor. So G is ample and E is effective. So in particular, there exists an E naught contained in the support of E such that E naught dotted with R is negative. So from this it follows that actually R is contained inside the image of this map of Kleiman-Mori cones. Oops. Of E naught into any bar X. So what we want to do is we want to restrict to E naught and apply the cone theorem in a dimension equal to 2. And this, I guess, is a theorem of Bogomolov and McQuillan. Let's see here. So we have basically two cases. Either E naught is invariant, or E naught is not invariant. Let's focus on the second case. So E naught is not invariant. One is like totally similar. Well, observe that KF plus E naught dotted with R is negative. And we can write K of F plus E naught restricted to E naught is equal to K of F E naught plus delta E naught. And this is by adjunction. Now, there exists an extreme array R naught inside any bar E naught such that, so I guess R naught is extremal and K F E naught plus delta naught negative. And such that R naught maps to R under the inclusion. Right. But the point is that now we apply the cone theorem for surface foliations. To see that R naught is spanned by a rational curve. So R is also spanned by a rational curve. Okay, so there's a bit of subtlety that I'm sweeping underneath the rug, is that we're a priori the singularities of the pair F E naught delta E naught might actually be worse than log canonical. And so there's a slight subtlety there that I'm sweeping underneath the rug, but you can get away this get around this problem using a few tricks. So it's not necessarily a serious difficulty. Also, I can't believe I forgot this, but I should also mention this whole story of the minimal model program has been worked out for surface foliations. So, apologies to everyone. I guess it's better late than never. And this was just a bunch of really amazing work by Mendez, Brunella, and McQuillan, and just a bunch of really great papers. So maybe I'll stop there, and then in the next talk, I'll talk about existence of flips for foliations. Thank you.